So here we're going to take a look at binding energy. It's the amount of energy we need to bind together the particles that exist inside of an atomic nucleus. So let's say we have the nucleus of a helium atom, 2 protons, 2 neutrons. The binding energy could be measured as the amount of energy needed to input to break apart that nucleus into separate particles that are no longer bound together. So here's some energy that will break apart these fellows into separate nucleons. That amount of energy is not the same for every element. So there's some very interesting experimental results that come from making these kinds of measurements. Let's say we take helium-4 and combine it with beryllium-8 to make carbon-12. This is a fusion reaction that occurs inside of stars. Well, if we look at the mass of these fellows, the reactants, and compare it to the mass of the products, we'd find out that the carbon-12 here actually weighs a little bit less than the total mass of beryllium-8 and helium-4. Now, the atomic mass units, yes, they do indeed balance. So 8 plus 4 is equal to 12, and in terms of atomic mass units, we're all good. But underneath those atomic mass units, we measure the masses very, very precisely. The difference in masses is very, very small. But if you take a look at Einstein's equation, E equals mc squared, the difference in masses, that could be related to the binding energy, so we can call it mb. So let's say that's the mass of the products, the carbon-12, minus the mass of the reactants, beryllium-4 plus helium-4. This will be less than 0. This will be a negative because the mass of the products is a little bit less than the mass of the reactants. That mass that's related to the binding energy is very, very small, but we take that small mb and we multiply it by c squared. C is the speed of light. That by itself is a very large number. We square it, it makes it even bigger. And we would get E sub b, the binding energy, and that's what we could add to this equation here. It's a small mass difference, but it's a very large energy that is output, and that's the energy that we get from the process of fusion. This is something that takes place inside of stars. The burning of helium and hydrogen and other elements is what gives us the energy inside of our sun. Let's take a look at another example. Let's take a look at uranium-235. Let's say it were to decay into thorium-231 plus an alpha particle. Again, the atomic mass units look balanced. 235 is the sum of 231 plus 4. But again, the masses of these fellows here is less than the mass of the starting material, uranium-235, and so we would get, again, some energy as output. But notice this is a little bit different. We're getting energy here by taking the U-235 nucleus and breaking it apart into separate things, while in a prior example, we took beryllium and helium and fused them together to get energy. And so there is a very famous diagram. We'll just erase the chalkboard here and draw it here, where we look at the binding energy per nucleon, not the total binding energy, but the binding energy per total number of particles in the nucleus. And that will be compared to Z, the atomic number, and we'll go from 1 for hydrogen out to 92 for uranium. And the curve looks something like this. There are some bumps along the way, but it rises very steeply up to iron 56. And then it levels off, but not precisely. It sinks a little bit as we head towards uranium 92. So up here we have iron 56 at the top of this binding energy per nucleon chart. Now it's kind of an odd chart, but we can divide it into two parts. Everything to the left of iron 56, the process of fusion will release energy. So that would be our example here, where we took something like beryllium and combined it with helium to make something heavier like carbon-12. So fusing these two guys together to make something heavier released energy. On the other hand, if we take uranium and split it apart to make smaller atoms, then in this case, fission will release energy. What we looked at before as an example wasn't really fission. It was well, I guess fission on a very, very small scale, but it was the decay of uranium into an alpha particle plus thorium. But here it's creating smaller, lighter elements that releases energy. So iron 56 is at the top of the heap. It has the highest binding energy per nucleon. If we have anything that's heavier than that, we can get energy by splitting the atoms apart. If we have anything that's lighter than iron 56, we can get energy by fusing the atoms together to make bigger atoms, but we get nothing out of iron itself. We can split it apart or fuse it together, and we would not get any energy out of those kinds of reactions because it has the highest binding energy per nucleon.